it is a section 14.3, partial derivatives. Before defining partial derivatives, we'll begin with a recall. For a function of one variable, y equal f of x, we say it is differentiable at a point A if this quotient has limit, and the limit is called the derivative of f at A. See this figure? This quotient indicates the slope of this secant line as h approaches 0. In this case, the slope, average slope, converges to this instantaneous slope. And we call this slope the derivative. For functions of two variables, the graph will make a surface. Now we try to restrict the graph with a plane, for example, parallel to x-axis, passing the point. Then it's like a cut the surface by using the plane. Then the intersection will be a curve. On the curve, we may try to find slope at this point. That is called the partial derivative with respect to x. So that we say that is f sub x. So we restrict the surface in a coordinated direction, x direction and y direction. And if we see curves, then along the curves, we try to find the slope at the point. So we call these slopes partial derivatives. Okay, that's the main idea. Now, mathematically, we can deal with the idea in this way. First, we fix y, say y equals b. Then, now, we'll deal with this one, f of x and b, and that one will make here the curve here in blue. And we say that is z equal g of x. Then for this one, we'll try to find the slope. So g prime at a is the same as here, limit h approaches 0, and this quotient. That is basically the slope at a of the function g. But g of x is the same as this one, so that we can write in this way. Now, if we look at this term, then that is the change rate along only the x direction, and y is fixed to be b. Once the limit exists, then we say that is partial derivative of f with respect to x at ab. Okay, for the partial derivative of f with respect to y, we can do it exactly same way. Now we fix x is a, then we consider capital G of y to be f of ay, and try to find the slope of capital G along y direction, and that is exactly this one. And once the limit exists, then we say it has a partial derivative in y direction, and the partial derivative is denoted by f sub y. Okay, let's try to solve this problem. Find f sub x 0, 0 when f of xy is defined in this way. Now, by using the definition, we start with that way, and y equals 0 now, and around the 0, so that is 0 plus h, and that must be 0. Okay, now we write down the detail. Okay, limit f h0, that's h, so that is third root of h cubed and 0, and minus f, okay, 0, 0 must be 0, and divided by h, right? Okay, but this term is h. So, okay, that is same as a limit h over h. For every h, it is always 1, so that the limit must be 1. So f sub x at the origin is 1. For f sub y, you can do it exactly the same way, because this is a symmetric with respect to x and y, and you will get again 1 for f sub y at the origin. Okay. Now we define partial derivatives in this way. If f is a function of two variables, then its partial derivatives are the functions f sub x or round f over round x, and f sub y is round f over round y, and they are defined in this way. And at xy, general point, f sub x is here in only x direction. We are trying to get the rate of change. So it is a x directional slope. And similarly, we can say f sub y is the y directional slope. The partial derivative with respect to x represent the slope of a tangent line to the curve that are parallel to the xy plane. And also for the partial derivative with respect to y represents the slope of the tangent line to the curve. Now, with this observation, we can find a rule for the computation of a partial derivatives. F is a function of two variables. Then, to find f sub x, we consider y as a constant and differentiate f with respect to x. The same way, to find f sub y, we regard x as a constant and differentiate f with respect to y. Okay, let's try this one. Okay, f of xy is given in this way. Then to find f sub x, we consider y as a constant and differentiate the function with respect to x. So for that one, we have 3x together. For this one, y, this one is constant. Only we differentiate with respect to x. So that is now 2x, and y cubed, that is constant. And this one is constant, so that it will be 0. Okay. Now, f sub y, for y directional derivative, here, that must be constant. So its derivative is 0. And now, x squared is constant. And for y cubed, its derivative is 3y squared. Now, for that one, minus 4y, right? Okay. Now, we have to evaluate at 2, 1, x is 2, y is 1. Then here, if we are using the point here, evaluating at 2, 1. Then, okay, x is 2, so that 12 and plus, now 4 plus 1, 4 times 1 is 4, so that 16. Now x is 2, y is 1, that is here 12 minus 4, that is, so that is 8, right? Okay. F of x, y is given in this way. Find the first partial derivatives of the function. Okay, exactly same way we can find f sub x and f sub y. For f sub x, now we consider y as a constant. So first, with respect to this one, we try to make derivative, which is cosine x over 1 plus y. Now, for that block, we make x derivative, then there must be 1 over 1 plus y. Right? Okay, how about f sub y? For that one, we are making derivative only with respect to y, considering with respect to x and considering y a constant. Okay. Now y derivative. Then first we consider this as a block, and derivative with respect to the block, that is cosine. This is a kind of chain rule, right? X over 1 plus y. Now for the block, we have to make y derivative with x being a constant. So that is same as now x over 1 plus y, that scatter. Somewhere we have to put negative. Okay. So that's the final answer. Find the first partial derivatives of that one. Okay. Now f sub x, x derivative, then that is y is a constant. So it is a form of x to the r. For that function, its derivative is r times x to the r minus 1. So here r is y. So y, x, y minus 1. Right? Okay, how about f sub y? Okay, if we consider this one as a function of y, then is an exponential function. So that is a form of this one. For this derivative, we have the function times logarithm a. You got this formula from calculus 1 in this way. For example, y equal a to the x. Then from here, we are taking logarithm. Then by using law, rule, we can get that is x times logarithm a. Now we make x derivative, then that is same as y prime over y equal logarithm a, only the constant remained. From here, y prime equal y times, but y is a to the x and logarithm a. So you got that formula, right, from calculus 1. Okay, we'll use the formula. Okay, so it is now in y direction, it is an exponential function. So its derivative must be x to the y, the function, and logarithm of the base. So natural logarithm, the base is x now. So that's the derivative. Implicit differentiation, you learned this one from in calculus 1. So this is a recall. For functions of one variable, and now y is a function of x, and once the equation is given implicitly, then you may get x derivative in this way. So it's a 2x from this one, and now first you are making y derivative, so the 3y squared and y x derivative. Of course, right side must be 0 once differentiated. Okay, so from this equation, you can get y prime by solving the equation. So that's the result. Exactly the same way, you can find the partial derivatives through implicit differentiation for functions of two variables. Now, z is a function of xy, and here the assumption is z is z of xy. Okay, now let's try to find z sub x and z sub y. Okay, and we make x derivative. Then from here, there is 3x squared. Y is another independent variable, so it is considered as a constant. So x derivative must be 0. And now from this one, okay, let's try to write down 0 for the second one. It's now 3z squared. First we make z derivative, and z for z x derivative, which is z sub x, right? Rather than like the prime notation, we are using partial derivative notation. Okay, now for that one, x is here and z involves x. So we have to use product rule. For this one, we make derivative, which is 6yz. And now for that one, plus 6xy, and that's z sub x. Okay, that is from the last term of the left-hand side, and right side must be 0. Now we can solve it for z sub x. So from here, okay, we have here and here. So there are 3z squared plus 6xy and z sub x. And we'll move these two terms to the right side. So the minus 3x squared plus 6yz. So divide by this term to get z sub x. That is now minus 3x squared plus 6yz divided by that term, 3z squared plus 6xy. For z sub y, you can do it similarly. Try to do it yourself. Okay, we try to find f sub x at 0, 0 for this function in problem earlier, and by using the definition. Now, we'll try to find this quantity by using the technique of finding f sub x and f sub y. That means, rather than definition, we try to use this rule to get partial derivative and see if it is convenient. Okay, now for given function, let's try to get f sub x, x derivative. Of course, function itself is the same as here, x cubed plus y cubed and third power. So the f sub x for this plot we make derivative, and 1/3 n x cubed plus y cubed n minus 1 minus 2 over 3, and here derivative this block with respect to x, which is 3x squared. Okay. Now that one can be written here, 3 1/3 cancel out, top is x squared, bottom is x cubed plus y cubed and 2 over 3. Now we have to evaluate this one at 0, 0. Is it easy? Not easy. So sometimes, rather than using the technique, sometimes you have to use the definition to evaluate the partial derivative. So the purpose of this problem is to emphasize the definition. Sometimes the definition is useful. Okay. Now, these partial derivatives can be easily defined for functions of more than 2 variables, 3 variables, 4 variables, arbitrary many variables. We can define partial derivatives. For functions of 3 variables, consider this function of x, y, z, and let's try to find f sub x, f sub y, and f sub g. Okay, f sub x. Now exactly the same way, we consider yz as constants. Then here, this is constant, y is constant, and x derivative, which will make y extra y, e to the xy, and logarithm z. Now have f sub y. This time we consider y the only variable, and x and z are constants. Okay, for that one, y derivative, and x will come out, e to the xy, and logarithm z. Okay. Finally, f sub z. Again, z is the only variable, so e to the xy must be a constant. And for z, if we make derivative, then that will be 1 over z. Okay, that's it. We'll continue in the second part. Thank you.